Good morning. I am continuing to work my way through DrPhysicsA's videos Einstein Field Equations for Beginners. At 41 minutes into that video, which I kind of have denoted here as 41.:10, he introduces equation 4, the contravariant transformation. Now you may find that at this point my terminology diverges with DrPhysicsA to the point where you're not even sure that we're really talking about the same thing. But the main difference in terminology, I think, is that I'm going to call this thing right here an outer product, whereas he calls it a tensor. As usual, whereas DrPhysicsA shows a single representation of an equation, I'm going to attempt to show two other representations, but this time I have a problem that hasn't cropped up before. In this situation, there is no way that I've been able to figure out anyway to maintain the order of the variables in the given form. The problem is that in the summation notation, it's clear that we are sum of producting the incrementing r terms by the incrementing r terms, and we're sum of producting the incrementing s terms by the incrementing s terms. But with matrix multiplication, you can't do sum of producting unless the two matrices are adjacent to each other. Here's the notation that DrPhysicsA gave for the covariant transformation. If we wanted to give it in the officially sanctioned Einstein notation, we would remove the implicit summation sign, which was important back then in the 1930s because every extra pin stroke led to more carpal tunnel syndrome. But if we want to put it in matrix multiplication notation, we can't just have the paired sums labeled twice. We have to have them adjacent to one another. Okay, now let's put in some arrows. Now I'm going to put in some arrows. So matrices are usually enumerated with the row first and then the column. So this T tensor over here is going to represent the nth row and the nth column of the matrix. So whatever happens here on the right-hand side has to match the left-hand side. So I will label the M going down and the N going across, going right. Down right, conventional matrix labeling, if I do say so myself. That's a mnemonic pun, if you couldn't tell. Now since these are Jacobians, this R has to go to the right, this S has to go down, just because it's got to be the opposite of whatever that arrow above it is. This R will go down, and this S will go to the right because it's got to be the opposite of whatever is over here. Going right and down will give you a sum of products. Going right and down will give you a sum of products. Now I'm going to use those arrows to create the matrix once, which would look like 1, 1, t sub 1, 2, t sub 2, 1, t sub 2, 2. The reason that's conventional is because it goes 11, 12, 21, 22. They're just like ordering the numbers to the right. I'll do this del y, del y, del y, del y, labeling them down 1, 2, 1, 2, and then over del x, del x, del x, del x, and label these to the right 1, 2, 1, 2, and then a sub 1 coming, let's see, yeah, a sub x1, a sub x2. This is actually a little bit quirky notation because that x, that 1 and 2 shouldn't really be separated from the x. This should just be x sub r, x sub s over here, rather than a sub x of r and a sub x of s. Then, of course, we've got b sub x1, b sub x2, and going over with, again, del y, del y, del y, del y, over, del x, del x, del x, del x, and this time we'll go to the right, 1, 2, and down, or wait, y goes to the right, down, x goes down, 1, 2, 1, 2. Zing! Okay, so I made it a little bit smaller so you can see the entire equation at once, but you see that now all of the matrix multiplication is set up so that it's ready to do in order. So as a reminder, this outer product of vector A and vector B right here will give you everything you need to do a dot product by summing along the diagonal, or a cross product by taking negatives and positives and stuff like that in different directions. It's not really everything you need, but it's an organized table. It's a table of products of each pair of components. So, okay, I'm going to admit something that may become untrue sometime soon, but I am not familiar with any definition of tensor that isn't sort of circular and unsatisfactory. What is a tensor, I ask? Well, I get the answer. A scalar is a tensor of rank 0. A vector is a tensor of rank 1. And the outer product of two vectors, is a tensor of rank 2. Yes, those are examples of tensors, but what is a tensor? Well, it looks like a tensor is a bunch of numbers or functions arranged in rows and columns. But we can add this qualification to that description that if we describe a tensor in one coordinate system, it is going to have a different description if we describe it in another coordinate system. I'm going to try something really simple and see if this is actually an example of the use of this equation. Then I'm going to try something more complex, keeping in mind that I have no real idea whether these are examples of the use of this equation or not. I'm going to try to convert 27 square feet to yards. I already know how to do this, and that's kind of why it's with conversion factors, and that's kind of why I suspect it might work here, or something at least similar to it. If y equals yards and x equals feet, then del y del x would be 1 yard per 3 feet. And if I were to write this equation, just the t11 part, let's say, t11 equals del y del x, or del y del x times a sub x, b sub x, which is going to be 27 feet squared. And then del y del x again over here, the del y1 del x1. We would have, that would be equal to just 1/3 times 27 times 1/3, which would equal just 3 square yards. Yards squared. Okay, the problem with that example was that it doesn't maintain that 2 by 2 appearance that I have up there, so that's why I made up this other example with 3 feet by 6 feet. if I have a 3 feet by 6 feet, we'll be able to consider these cross terms, and we'll have 3 feet by 6 feet, and these are going in the same direction. I think this would be the format for del y. It would be 1/3, 1/3, 0, and 0 times 3, 0, 0, 6, 1/3, 1/3, 0, 0. Now, where are these zeros coming from? Here, 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 and here. Well, let's say I have vectors measured east-west and north-south. Well, let's say I have vectors measured east-west and north-south. So the 3 is going north, or no, the 3 is going east, and the 6 is going north. So if I change my measurement scale in the north-south direction, it has no effect on my readings in the east-west direction. So this is strictly the change in measurement in the east direction compared in feet compared to yards. This is strictly the comparison of measurement in feet to yards of measurement in the north direction. Let me say that again. This 1/3 is the effect of changing our east-west coordinate system from feet to yards on an east-west measurement. This 0 is the effect of changing our east-west coordinate system from feet to yards on a north-south measurement. It has no effect at all to change the east-west coordinate system on a north-south measurement. This 1/3 is the effect of changing our north-south coordinate system from feet to yards in a north-south measurement. So those match. Anyway, at the end, let's multiply all this out. So the 3 and the 6 become 3 times 0 is 0, 3 times 6 is 18, 0 times 0 is 0, and 0 times 6 is 0. Then we'll take 1/3, 1/3, 1/3, 1/3, 0, 0, 0, 0, and that ends up being just 1/9 of 18, so it'll be 0, 2, 0, 0. Okay, one thing to remember about what we did, this was x, x, this was x, y, this was y, x, this was y, y, and it was definitely 3 feet or 1 yard in the x direction and 2 yards in the y direction. So I could see, I was kind of expecting when I worked this out for it to be a 2 here and a 2 here. I was a little surprised when that became a 0. If I had gone the other direction with it, with the 0, 6 first and the 3, 0 second, then I think I would have ended up with 0, 0, 2, 0 at the end. So in this example, regardless of how we interpret this result, this only emphasizes the fact that equation 4 is not commutative in any way, shape, or form. So
AMBN, well, that's just the tensor TMN in the Y frame of reference, because that's what we selected here. And that is going to be equal to the sum over R and S. That's not quite the right way to do it, but essentially you've got two sums.
And And I think that's the key phrase there. This is not quite the right way to do it.
Some terms here, which I'm just going to simplify here, multiplied by dym by dxr, and then you've got a dyn dxs times axr bxs. That's that term and that term.
And the reason I say that that's the key phrase there, that it's not quite the right way to do it, is that this is not the things that he just did are kind of illegal. It's not. This is not a commutative operation. And there is one correct way of doing it. I am not sure that the way I just did it actually is the correct way of doing it, but I think it is. I think that this equation here is correct, and in order to make this multiplication, this actually has to be a dot product between the vector that comes out of this and the vector that comes out of this. And in order to do the dot product, you take this vector times the transpose of this vector. And in order to do that transpose, you have to reverse the order of those things. So in this example, why did this come out to be 2 and this come out to be 0? Probably because that's what actually happened. I built 1 in the x direction and 1 yard in the x direction, followed by 2 yards in the y direction, and I did not build anything in the y direction followed by the x direction. So this is kind of keeping track of some kind of order. Down here I built 6 yards in the y direction followed by 3 yards in the x direction. I did not build in the x direction followed by the y direction, so this is 0 and this is 2. In fact, if I were to follow something like this up with a cross product, we'd actually end up subtracting those two terms. If you want to do a two-dimensional cross product with this outer product, you can use the two-dimensional Levi-Cevita symbols in the antisymmetric matrix 0, 0, 1, -1, and the use of the 2D symbol is relatively uncommon, although in certain specialized topics like supersymmetry and twistor theory, it appears that in the context of two spinors, the 3D and higher dimensional Levi-Cevita symbols are used more commonly. But anyway, this outer product of the 1 yard and 2 yards would naturally be followed up by the application, perhaps, of the Levi-Cevita symbol, and following it up by that Levi-Cevita symbol, 1, -1, would probably give you the area of the associated region. So even if I had said 1, 2, and said then converted and then used the Levi-Cevita symbol, I would find the area of the associated what do you call it? Parallelogram. I'm sorry, I should be more clear. This would be like let's say 3, 1, and this would be 6, 2, something like that. So that this is coming over 3 to the right, 1 up. This one's coming 6 to the right, 2 up. No, I want 2, 6. 2, 6. So it goes over 2 to the right and 6 up. And then you could figure out this outer product of that, then apply the Levi-Cevita symbol to find out the area of that parallelogram. So that was some ideas for the use of equation 4. I'm going to leave that for now and say ta-ta.